All right, let's continue with section 7.4, working with the trigonometric functions. We'll look at some fundamental identities as well as the domain and range of the trigonometric functions. All right, so some fundamental identities here that are very useful. And if we were in a pure trigonometry class, we would go way more in detail with these, but I want to just do a couple of examples here. All 6 trigonometric functions can be written in terms of sine and or cosine as follows. So tangent of your angle can be rewritten as sine over cosine. Cotangent can be written as cosine over sine, and then these ones we already pretty much knew, that the cosecant is the reciprocal of sine and the secant is the reciprocal of cosine. Okay, so all of the trigonometric functions can be written in terms of sine or cosine. And the reason why we can quickly prove, let's just think about tangent. Tangent of an angle is defined to be the y components divided by the x components. And hey, guess what? The y component on the unit circle, that's sine of your angle. And the x component, that's cosine of the angle. So yeah, tangent is exactly the same as sine over cosine. Okay, and similarly for cotangent. So let's just do a simple example here where we can actually simplify this expression here. We've got secant of t divided by tangent of t. So the strategy here is if we just turn this expression into just a bunch of sines and cosines, then there can be some canceling and some simplifying that can happen, and we can get a simpler statement. So let's do that. Secant, let's go ahead and rewrite that. The secant is 1 over cosine. And then the tangent is sine over cosine. Okay, so now we have a fraction divided by a fraction, so we can flip and multiply, and we get cosine over sine when we flip and multiply. And so now straight across the top, we have cosines are canceling, and so we get 1 over sine. And then to make our final answer as clean as possible, 1 over sine is the same as cosecant. Okay, so yeah, in a regular trigonometry class, we would spend a lot of time going with a whole bunch of different fundamental identities, proofs to be able to simplify certain things. But this is enough for us right now just to be able to realize that you can try to manipulate these to simplify them. And again, moving into a calculus class, being able to manipulate trigonometric expressions like this is a really good thing so that you can make stuff easier to work with. Okay, because secant divided by tangent, it's way better to work with just cosecant because they are the same thing. All right. Further work with trigonometric functions. So let's just do this example here. I'll show you maybe a couple of different ways to work on this one. Find the values of the other 5 trigonometric functions. Okay, so, and then we'll talk about the range of the trig functions in just a second. All right, so here we go. If cosine of t is 12 over 13 and t is in quadrant 4, find the value of the other 5. Well, it's definitely a good idea to get a picture going. And it says quadrant 4, so I'll kind of exaggerate it so I've got some space in quadrant 4. This is one of the options for how to do it, and this is actually kind of the option that I preferred in the past. If you've got your angle t here, or perhaps that would actually be like maybe t prime for the reference angle, but it doesn't matter. We can use the angle t right there. Since cosine is defined as the adjacent over the hypotenuse, we can actually label it as 12 for the adjacent and 13 for the hypotenuse. And so we're missing the y value. So what we can do, there's 2 different options. One is we can work out the Pythagorean theorem right here, or we can use the Pythagorean identity where we wouldn't ever even need to draw a picture. Okay, I'm going to do maybe both ways to really emphasize, because the visual way, this is how I did it when I first took a trigonometry class. So if we work out the Pythagorean theorem here, it would be what? 12 squared plus y squared equals 13 squared. Okay, so we have 144 plus y squared equals 169. And we have y squared equals 25. And so taking the square root of both sides, we get y equals, and don't forget, it's technically plus or minus when you solve by taking the square root of both sides. So this is where it's really, really important. Because we're in quadrant 4, is this the positive direction of y, or is this the negative direction of y? And it's extremely important. You'll get all your answers wrong if you don't label these properly. This is the negative direction of y, so we have to pick -5. Okay, now that we have that worked out with a Pythagorean theorem, we can find all 5 of the other ones. So we can use our silly old rules of like the SOHCAHTOA and stuff like that. So I'll quickly go through and do those. So we have cosine t already, so sine of t. Okay, so that's going to be opposite over hypotenuse, -5/13. We have cosine, so then we can do tangent of t. That's going to be opposite over adjacent, -5/12. Okay, let's do cosecant of t. That's going to be the reciprocal of sine, so that's -13/5. Secant of t, that's the reciprocal of cosine, so that's 13/12. And cotangent of t, that's the reciprocal of tangent, so that's -12/5. Okay, so we got them all. If drawing a picture isn't your cup of tea, we can actually use the fundamental identities to work these out. Okay, so if we're given cosine, I can very, very quickly find out sine by using the Pythagorean identities. Okay, so I'll kind of do a little separate. Okay, so with using the Pythagorean identities and the fundamental identities, remember that sine squared t plus cosine squared t equals 1. Super powerful identity here. Okay, so if we're given cosine of t, we can find sine t using this. So if I did sine squared t plus, now cosine squared, cosine comes out 12/13. So you put the 12/13 in there and it's got to be squared. Okay, so now we can keep going, solving for sine. When you square a fraction, you square the top and the bottom separately. So we want to subtract the 144/169 from both sides. And so we have sine squared of t equals, okay, so you can turn that 1 into like 169/169, and then we would subtract and get 25/169. Take the square root of both sides, and we get sine of t equals, now technically it's plus or minus, but since we're in quadrant 4, you might remember this little thing, ASTC, all students take calculus, the little acronym to help us remember which quadrants have which trig functions are positive. So since we're in quadrant 4, we know that cosine is positive, which it was given to us as positive, but sine is negative. So we must choose the negative and then the square root of the top and the bottom separately. And we got the same answer from before, but maybe that feels like a little bit more work. I don't know, it kind of depends on what your preference is. The Pythagorean identities are awesome. Drawing the picture, that helps us as well, but notice that in either case, we technically had to use the Pythagorean theorem. Okay, so then once we have the sine, let's continue using the fundamental identities. Okay, remember that tangent is sine t over cosine t, and we have both of those now. So we can do tangent is sine of t, which is the -5/13, that's a 3, divided by cosine of t, which is the 12/13. Okay, and then flip and multiply, we have 13/12. And so straight across, sorry, this is a 13, it looks pretty bad, but the 13s will cancel, and we get that tangent of t equals -5/12. Is that the same answer? It is. Okay, so Pythagorean identities, I'm also using the fundamental identities. okay, for the tangent being sine over cosine. Okay, and no, okay, so now we've got sine, cosine, and tangent, and so all the reciprocals would follow immediately with the fundamental identities. We instantly know based on sine, we know cosecant is the reciprocal of that, so negative 13 over 5. We know tangent, cotangent of t would be negative 12 over 5 for the reciprocal, and then cosine again, secant would be the reciprocal of the cosine. So anyways, you can get these answers in two different ways. I think the way that I did it when I was first in trigonometry years ago, I liked drawing a picture and working out the Pythagorean theorem like that. But the Pythagorean identities and fundamental identities, this is more of an algebraic way of doing it. And this is really cool as well. About the same amount of work probably, but you got to learn these new identities. All right. You know, I really want to emphasize the quadrant that you're in makes a huge difference. So when you're solving these equations and you take the square root at the end, the plus or minus option totally depends on which quadrant you're in. So that's why sometimes the picture helps us as well. Or you can remember this ASTC thing to remember which trig functions are positive in which quadrants. Okay. So let's just talk a little bit. I'm not going to do any like major big examples. I just want to talk about these because this is very important when we move into the next section, because we're going to start doing a little bit of the graphing of the trig functions, and it's important for us to understand the range of the trig functions as well as what a period means. So we'll get into more detail in that in the next section, but let's just talk about it a little bit right now as kind of a preview. So the range, okay, so just the outputs, right, the y values, the range of the sine and cosine functions is -1 to 1. Okay, and if we go back to the unit circle, let me just go look at the unit circle here. So the y values and the x values are all just the components of these pieces here. So 1, 0, okay, let's think about cosine. Cosine starts at 1. Then this gets a little bit smaller, 1/2, a little bit smaller, and then it's down to 0. Okay, then it's negative, getting a little bit bigger negative, a little bit bigger negative, and it reaches -1. But then it shrinks back down, getting a little bit smaller negative, a little bit smaller negative, and then down to 0. And then it gets increasing a little bit, and then back to 1. Okay, and similarly with the sine, the highest it ever reaches is 1, the lowest it ever reaches is -1. So the sine and the cosine, they are stuck in between -1 and 1. Okay, so that's going to be pretty important if we're trying to figure out different possible values for sine and cosine that can come out, or if we're trying to talk about what the graph of those functions is going to look like. Okay, the range of the tangent and cotangent functions is -infinity to infinity. You can actually have any real number as an output for the tangent and cotangent functions. And the reason why that happens is that possibility of dividing by 0. Okay, so for example, if you were going to try to do the tangent of 90 degrees, that's going to be 1 over 0. And so when you divide by 0, we say undefined. But if you're getting infinitely close to that 0, so that the x value is actually like 0.00001 or something like that, when you do 1 divided by something super tiny, the result is super big. Okay, so you can convince yourself of that. Take your calculator, do 1 divided by, and if I'm not picking 0, I'm picking something tiny, tiny bigger than 0, like 1 divided by 0.1. That's going to come out 10. 1 divided by 0.01, that's going to come out 100. 1 divided by 0.000001. So the point is, the closer that you get to 0, the bigger tangent will get. Okay, and then similarly on the other side, if it's a -1 divided by stuff that's really, really close to 0, you're going to get really, really big negative numbers. Okay, so the tangent and the cotangent, they both have that possibility of coming out any real number as big or small as you want. So the range of the tangent and cotangent functions, they can come out anything. Okay, the range of the secant and cosecant functions is a little bit strange, but let's think about this. Secant and cosecant are reciprocals of sine and cosine. Okay, cosine and sine, respectively. Okay, so if the sine and the cosine have to be stuck in between -1 and 1, if you do reciprocals of any of the numbers in there, it's going to send them outwards so that you're not within -1 and 1. So let me just do a quick example for that one. If I had, for example, how about, let's do one that's really easy to understand. Let's think about sine of pi over 6, for example. Sine of pi over 6 is 1/2. Okay, so sine of pi over 6 is 1/2, and so that is within our range, right? 1/2 is between -1 and 1. If we were going to do cosecant of pi over 6, it's the reciprocal of that. And that comes out 2. And that is no longer within this range of -1 to 1. It's actually in this section here, it's greater than 1. Okay, and so that's going to happen with any of the values that you pick to plug in for sine and cosine. If you try to plug in, like, how about sine of 0, and that comes out 0, if we did cosecant of 0, that's going to be 1 over 0, which is undefined. And so with the same argument that I used for the way that the tangent and the cotangent, if you're not going to plug in 0 exactly, but you plug in really, really, really close to 0, that's how you can get these infinities. So you can end up having really, really large or really, really small numbers coming out. Okay, and then if you did something that was like right on the quadrantal, like sine of pi over 2, that's 1. Cosecant of the pi over 2 would be the reciprocal of that, which is still 1. Okay, so you can still have the 1 and the -1, but if you pick anything that's less than 1, which would be somewhere in between the -1 and 1, whenever you do the reciprocal of something less than 1, you get something greater than 1. So that's why the secant and the cosecant functions end up splitting out, and you get that their ranges have to be on the outside of that interval, -1 to 1. But it includes the -1 and it includes the 1. Okay, so that's just a little note just to get us kind of warmed up thinking about the range of these things. Let's talk a little bit about the period. Okay, so a period is just the shortest interval over which a function completes a full cycle. Okay, so there's lots of different types of periodic functions out there. But all of the trig functions are periodic because we imagine that we're going around the unit circle, and with coterminal angles, you can go around the unit circle again and again and again and again. And so all of these trig functions are going to be periodic because you can get the same values as you go around more than once in either direction, in the positive rotation or the negative rotation. Okay, so the period of the sine, cosine, secant, and cosecant functions is 2 pi. Okay, that makes sense. It takes 1 full revolution. Remember that 2 pi is 360 degrees, so that's 1 full time around. And so the whole period of the sine, cosine, secant, and cosecant functions, they will complete 1 full period as you go around the unit circle once, and then it will repeat when you start your second time around. The period of the tangent and cotangent functions is actually just half of that. And it's kind of an interesting property, and we'll see that in action when we start graphing these things. But tangent and cotangent, they actually complete all of their different possible values by just going halfway around. And then they repeat again on the second half. So let's think about this just a little bit. Let's just look at sine just for simplicity. Let's think about y equals sine, and I'm going to use the variable x now if we start talking about functions where we're plugging in real numbers. Okay, so don't get too confused. We're plugging in the letter that you plug in. You can use a theta, you can use a t, you can use an x. It doesn't really matter what letter you want to use, but I'm going to use x now because we're thinking about these as like x comma y for different functions. Okay, so on the unit circle, this one's pretty easy to understand. If we start plugging in different values, and there's all kinds of cool ways that we can do this, and we'll move on to this into the next section when we're graphing these in more detail. But on the unit circle, if we start plugging in different values for sine, we're going to start off at, and actually it's probably a good idea to think about the picture that we already had. For the sine values, they're the y components. So you start at 0, you go up to 1/2, root 2 over 2, you're covering these values and you reach up to 1. Okay, then sine comes down and it's approaching these values and it comes down to 0. then it's going to sweep through the negative versions of all of those down to -1, and then it's going to sweep back up and finally finish the rotation once it comes back to 360 degrees. Okay, so there's cool little animations where the sine value are the y values and the y values and the y values, and it comes all the way back around. And so if you were going to try to make this on like an xy axis, it's like all of the y values end up going up like this, and then they kind of repeat, and then they finish once you reach 2 pi. Okay, so you've got all of these different possible y values right here, and then it still keeps going and it still keeps going and it sweeps out, and you finally finish at 2 pi, and then it repeats once you go around the unit circle again, or it can repeat if you go back around the unit circle in the negative direction. Okay, so sine takes 2 pi to repeat. For tangent and cotangent, there's a little bit of a difference here where tangent is it's all of the y over x values. So as you keep going, tangent ends up having some weird little properties, and I'm not going to get into too much detail yet because I don't want to spoil the surprise. We're going to start graphing those in the next section. But tangent, remember that tangent, it starts at 0 because we've got 1, 0, and it's going to be 0 divided by 1. Okay, once you reach up here for 0, 1, tangent reaches a little problem, the undefined moment right there. So if we were going to start trying to graph all of the different possibilities, tangent's at 0 right here, and then it's increasing, increasing, and increasing, and then once we reach pi over 2, it's actually increasing in such a way where it takes off to positive infinity, and there's no possible way that you can actually ever reach pi over 2, because that's where you're dividing by 0. Okay, and if we went in the negative direction, because tangent's an odd function, it has this symmetrical property where it's heading towards negative pi over 2 eventually. At negative pi over 2, it's the same as 3 pi over 2, and that's 0, -1. And so we end up with the negative infinity version on that side. Okay, and then if you would start repeating over here, tangent actually repeats itself. We get another 0 over here at pi, and then at 3 pi over 2, we end up with that other problem of dividing by 0. Okay, so we got a 0 at pi, and then we have another problem of dividing by 0 at 3 pi over 2. And so anyways, notice that tangent definitely behaves in a little bit of a different way, and the distance right here is pi. And then another distance right here for a full period is pi. And tangent actually repeats that same shape every pi distance on the x-axis. Okay, so again, I'm kind of just doing some arguments here to show you. We're going to get into way more detail once we start graphing these things, but I wanted to do just a little bit of a preview about what we're talking about with the different ranges of the sine and cosine graphs, and then the different periods of all of the different graphs here, sine, cosine, secant, all of the reciprocal identities as well. Okay, well, that's going to finish off section 7.4. Again, very important to get comfortable with that unit circle and be able to quickly evaluate these trig functions based on the unit circle. And just over the many months that follow, you'll probably start to memorize certain things, so you eventually don't even need the unit circle anymore. All right, anyways, that finishes off section 7.4. Hope you have a good day.